Today's first lesson, math. Of course you have to be subjected to that particular brand of torture before anyone has really woken up. Your teacher arrives carrying a cup of coffee atop a cardboard box, announcing you're going to play a game. Brilliant. Except then he adds coffee as the prize. Beautifully caffeinated coffee, and suddenly, everyone is very interested. You gather around the box to reveal something like, Ned the snake? The teacher brushes past questions about exactly how poisonous Ned is, and explains the rule. You only need to find a moment where none of Ned's stripes line up with the same colour on the base of the box, like how this is overlapping here, or this here. Ready? Everyone quickly gives up. In fact, you can go back and pause this video to see it's impossible. But why? As it turns out, Ned isn't just here for fun. He's a pretty good representation of the Brouwer fixed point theorem in one dimension. This states, every continuous function f mapping a compact convex set into itself has a point where f of x equals x, which can be shown intuitively using this graph. Let me explain in English. So the x-axis is equal to the stripe on the box, no matter its size, say 60 centimeters. These two lines, the fixed interval, are the edges of the box, showing all the horizontal space Ned can occupy. Here, fixed interval essentially means compact convex set, the space stuff is allowed to be in. The y-axis shows all the places each point on Ned could be, so is the same size as the x-axis. This line, f of x equals x, shows all possible places where each point on Ned could line up to the same point on the stripes, all possible fixed points. Finally, this line shows where Ned is. Right now, he's turned opposite to the stripes, so the line is the opposite diagonal. Because this line shows where Ned is, and this one shows all possible fixed points, the place where they cross is the actual fixed point. This is where the phrase continuous function comes in. It's important Ned is a single continuous snake. If there were two smaller snakes, the function isn't continuous and these lines might not cross. The same is true if Ned escapes the box. The set isn't mapped into itself, so there might not be a fixed point. What if Ned eats lots of mice and looks like this? That's fine. He's still in one piece and fits inside the box. Just. Well, what if she is pregnant? Ned Jr. only has a fixed point if she is a clone. So you're probably wondering why I'm explaining this instead of something innovative like gene therapy or quantum biology. Of course, this doesn't just apply to boxed snakes. As well as being vital to topology, differential geometry, and even economics, the most popular use of the Brouwer fixed point theorem is used by everyone, regardless of mathematical ability. Every time they visit a zoo, hospital, airport, park, and almost any large building or space. You are here, science rely entirely on this theorem. Presuming the map is accurate, the arrow points to a single point exactly over the same point on the ground. Let's take this world map. Wherever I go on Earth, there will be a fixed point somewhere on the paper. Right now, it's about here. However, there's no fixed point on this map of Egypt, as the set isn't mapped into itself. In other words, I'm not in Egypt. The theorem applies to further dimensions too. Fill a cup with water, or any other liquid, then stir it continuously. The theorem states there's at least one point in each of these cups in the same place now as it was before being stirred. This remains true until the liquid is drank or spilled. In fact, this is exactly how Lucien Egbert's Jean Brouwer originally hypothesized his theorem. By stirring a cup of coffee. Many mathematicians have provided proofs to the theorem since, but what still remains a mystery is how Brouwer came up with this early in the morning, before he drank the coffee.